If I run this C# code, it'll output woof, even though my object is declared as an animal, not a dog. The reason this happens is because of an object-oriented programming principle known as polymorphism, which basically means that the object can behave as a different type, a dog, while being seen by the compiler as an animal. This might be useful for a scenario where I have an API that takes any type of animal and needs it to use its sound somehow. It doesn't care what sound it makes, but it also wants to be able to accept multiple different types of animals. In this example, I can pass a dog, cat, or any other object whose type inherits from animal to the method, and it'll work using that animal's specific sound. But how does the program know that I want the dog's implementation? Well, maybe it's because I instantiated it as a dog here. That could be a possibility, but what if I had a non-deterministic program like this? Sometimes the animal is a generic animal, sometimes it's a dog. In this case, the compiler is unable to know what the concrete type of the object will be, but the runtime environment obviously does, so maybe it's using reflection? Well, that can't be it either, since this benchmark shows that running the example with reflection has a different runtime than without it. So, what's supporting this mysterious behavior? We need a mechanism that can point to the overridden function at runtime without having the overhead of something heavy like reflection. This is called dynamic dispatch, where the target address of the method call is selected at runtime rather than compile time. And the most common solution that programming languages supporting runtime polymorphism use is called a virtual function call. But before we get into that, let's look at how a normal function call might be dispatched. In this code example, I create an object of type person and call the sayHello method on it. Since sayHello isn't marked as virtual, this won't be dispatched dynamically as a virtual call. Instead, the call target will be bound at compile time. When the program is being compiled, the compiler knows that the program will definitively call this function rather than another one. And so it can directly encode the address of person.sayHello into a call instruction in the outputted code, and make a direct call to that target without having to worry about the state of the object at runtime. But in a non-deterministic example, it's impossible to know what type my animal is at compile time because it could be different in different runs of the program. So we have to use something that can definitively tell the type of the object, something that would utilize the fact that the object was created with either the dog or cat constructor to add a sort of signature to the object. When an object with virtual methods is instantiated, the compiler emits code to embed a special pointer in the object as a hidden field, called a virtual method table, or vtable for short. The vtable is essentially a list of the addresses of overrides for the object's runtime type. In this example, our base class only had one method. So if we instantiated a base animal, we would get a vtable with a pointer to animal play sound at index 0. The vtables for dog and cat might look like this. So regardless of what the variable is declared as in the code, real animal, dog, and cat objects will contain their respective vtables as an object field. Now, let's add an animal class who doesn't have a specific sound called unknownAnimal. Since unknownAnimal doesn't override animal play sound, its vtable would just have a pointer to the parent's virtual function, animal play sound. Now that we have the compiler embedding vtables into objects when they're created, we have the information we need to call the correct method and override at runtime. Instead of making a direct call like we would with a non-virtual method, the code will instead load the object's vtable, index the vtable at the proper index for the desired method, and make an indirect call to the address at that index. And that's essentially how virtual functions work. There are a few performance hits that virtual functions take though, since the program has to load the vtable, adding more instructions, and also making it harder for the CPU to predict the next target address, which prevents it from loading the next few instructions early. Virtual functions also prevent the compiler from applying optimizations like inlining, because the target address is often impossible to know at compile time. So, back to our original code example. This works because the .NET runtime embeds a method table, effectively a vtable, into all .NET reference objects, and thus the method playSound can be looked up and called efficiently at runtime. And that is the mechanism behind your favorite polymorphic objects. Thanks for watching, and I'll see you in the next one.